time to discuss one of the key concepts which is quite useful while programming, and this idea of how to convert what happens when one converts signed number, signed integer to an unsigned integer, and what happens when it goes other way around, that is a signed integer is converted to unsigned integer. To start explaining, before we start explaining that, let's start with this simple example. Here we have, in a C program, suppose we have a signed character which is 1 byte, x variable defined, and it's equal to -123. The bit pattern for -123 would be 1 followed by 3 zeros, 0, 1, 0, 1, or in hex it could be 85. So if you convert this to decimal, the first bit in signed encoding is obviously a signed bit, so the weight is negative, and rest of the bits which have one value contribute positive weights. So it turns out the value is indeed -123. Now suppose this x is equated or assigned to y, which is also a 1 byte data type but unsigned. So that means it uses unsigned encoding. Now the question is, what happens when we read y again? In most of the C implementations, what happens is that the bit pattern remains the same, but the interpretation of the value changes. So for example, what I mean by that is that the bit pattern of x, which is 1, 0, 0, 0, 0, 1, 0, 1, would remain same. But this time, if we read value of y, it will infer this bit pattern as if it was encoded via unsigned encoding. The reason being, the value has been defined, the variable has been defined as an unsigned variable. So this, instead of this now being a signed value, it will contribute positive weight because y is an unsigned variable. So this will contribute as 2 raised power 7 plus 2 raised power 2 plus 2 raised power 0, which in turns amounts to 128 plus 4 plus 1, which is 133. So the same value of -123 when assigned to unsigned variable of size 1 byte turns out to be 133. Now there's an interesting relationship between these two values. We had, in our example, x was -123 and y was 133. Now we need to remember that we are talking about data types which have same size. So here length of the size is 8 bits or 1 byte. Now there's one crucial or key property these encodings have, that when you convert one to other, the modulo or the modulus value of x and y is always equal to 2 raised power w. That is, the difference between these two is 2 raised power w. W here is 8, so this amounts to 256. That means that if we take amplitude of x and y, that is, or absolute values of x and y, the sum would always be 256. So if you, for example, know the value of x, here it is 123 plus y, you could always calculate y. So y would be 256 minus 123, and that is 133. Same holds other way around. If you know already y, you can calculate x. There's another key trick which you might find useful during dealing with integers in programming, and that is that, say for example, suppose you have a number minus 123 and you manually want to find what is the bit representation of this. And it's quite easy. The trick is it's a trick. The proof is beyond the scope of this video, but the trick says that if you first need to represent the binary representation of 123. We already know how to calculate that, so I won't go into calculations, but it is this number. You do it by simply dividing this number by 2 and storing the remainder. And now that you have all the reminders, you read them in reverse order. So it is 1 1 1 1 1 1 1 0 1 1 1 0 1 1. Because it's an 8-bit data type, so here we appended 0 in the front. Now the first step is to convert the value to its corresponding binary number. So once you find the binary value, then you flip it. So the first step is to flip it. And then the second step is to add 1. So the first step is to flip the number, and then the second step is to add 1. One of the key things which comes up now and then while dealing with integers is what are the upper limits of unsigned encoding of a particular data type, and what are the lower limits for signed encoding of another data type. Now and then you would come across a situation where you will need to calculate those or deal with those, and it makes sense to kind of generalize these situations a bit. And for that purpose, let's say we have a 4-bit number, for example 1110. Now in 4 bits we can have 16 combinations, so each bit can either be 1 or 0. Let's represent these each bits by a variable. For example, the first bit is x0, second bit is x1, third bit is x2, and fourth bit is x3. Now x0 can be either 1 or 0, and same holds for x1, x2, x3. Let's represent this bit pattern by another variable called x4. For example, we have 1110 as an example. Here x0 is 0, x1 is 1, x2 is 1, x3 is 1, and if we calculate, it is 14. So if we generalize, for example, for a W-bit data type, W-bit data type could be, for example, a 64-bit or 8-byte data type, and in that case W is equal to 64. Let's generalize this bit pattern. So if we have a W-bit with data type, then we can have a binary pattern x vector, so we can call it a bit vector with each bits here. We start with index 0, so we call the first bit as x0. So obviously the most significant bit would be W minus 1. Now in signed encoding, the most significant bit is a signed bit, and obviously the weight is negative. Now our aim here is to generalize how to calculate the limits or bounds of values a particular width data type can have. Say for example, let's start with signed encoding. Now in signed encoding, if you have a number and you want to find the lowest number, obviously for the lowest number this bit has to be 1 because it contributes negative weight, right? So because the lowest number obviously would be somewhere down the line which starts way back from 0, so obviously the first bit would be 1. and the rest of bits, these bits would contribute obviously nothing, because we want the value to be 0. So obviously the generic, if we have to represent it with a function, it would be weight of this bit. It is 1 and rest is 0. So the weight of this is 2 raised power w minus 1 and minus. So this is always the lower limit of w width data type. Say, as an example, if we have 1 byte, w is equal to 8. So lower limit would be minus 2 raised power 7, and that is minus 128. Now if w is equal to 32, so the lower bit would be minus 2 raised power 31. Now let's calculate the upper limit. Upper limit for signed encoding is quite interesting. Here the negative bit would have to be 0 and rest of them have to be 1, because we want the highest number that could be represented by our value, right? So the function which could represent the highest value would be summation of all these weights. So that would be 2 raised power w minus 2, 2 raised power w 3, 4, and 1, 0. Now with binomial theorem, this amounts to minus 2 raised power So with binomial theorem, we can compute this. Binomial theorem is beyond the scope of our discussion, but this amounts to plus 2 raised power w minus 1 minus 1, and this is our upper limit. Now let's see what, as an example, w is equal to 8. Now this upper limit would be 7 minus 1, which is 128 minus 1, 127. For 4 bytes, it would be 31 minus 1. Now, what about unsigned encoding? For unsigned encoding, it's quite easy. The lowest number for unsigned encoding is obviously 0. All the bits would be 0, so 0. But the highest number, all the bits, including this one, would be 1, right? So we can calculate this. This time even the first bit would contribute. So this would be with binomial term w minus 1. So the highest value which an unsigned data type of w bit width can represent is 2 raised power w minus 1. So it amounts to, for example, for 1 byte, 2 raised power 8 minus 1, which is 255. And for 32 minus 1. Well, it's hard to calculate this, but you get the jinx of it. So every time you convert from unsigned to signed or signed to unsigned, you just need to remember that the bit pattern remains the same, but the inferred value from that bit pattern changes. Obviously, that also means that if you for a second imagine 3 worlds with signed numbers, binary patterns, and unsigned numbers. Let's say width is 4, so signed numbers will be from 7 to minus 8, and the highest in binary would be, for example, this here, and unsigned would be 7 to 15 and somewhere 0, 1, 2. Yes, so one important property of both these encodings is that every time you convert from signed to unsigned or unsigned to signed, there is always a one-to-one mapping. There is no ambiguity here. So what I mean by that is that 7 will just have a unique representation in binary, and if you infer it in unsigned, it will be the same number. It will never be two numbers. Say for example -8. So there would never be an ambiguity, and there is always a mapping from each number to other set. If you recall, the difference between unsigned and signed is always 2 raised power w. But if you want to graphically see what is happening, you might. So if you, for example, have, this is our baseline and the value is 0, signed numbers usually will have values from both sides of this 0 baseline. They will have negative values, and it will go almost to -2w minus 1 all the way up to 2 minus 2w, 2 raised power w minus 1 minus 1, and minus 1 would be somewhere here. And on the other hand, unsigned numbers are always positive. They go all the way to 2 raised power w minus 1, right? Now, every time you need to, the conversion happens, always the signed negative numbers map to this portion of signed, unsigned spectrum. So this always maps to that. What is happening here is, for example, let's say -1. -1 for 4 bits is 1, 1, 1, 1, right? Now, what would be this if it was an unsigned number? This would be 15. Now, the highest number is 7. Here as well, 7. And the 15 would be here. So this point for w is equal to 4-bit would always map to 15. And this value here, which is for w is equal to 4, the lowest value is 1, 0, 0, 0. So this is, in unsigned value, it is 8. So -8 would always map to this point. But all the values which are less than 7 would have a straight mapping. And you can even represent this mathematically. So for example, every time you have an signed number which is greater than 0, the corresponding unsigned number would be same, right? If x is greater than equal to 0. But every time x is less than 0, the corresponding number would be x plus 2 raised power w. So this could be the mathematical formula of what is happening here. On this direction, we are converting this x here is a signed number. So every time signed number is greater than 0, this portion, it has a direct mapping here. So fx is x. So all the numbers here have a mapping here. But every time the value is below 0, it has a mapping for a bigger number on the unsigned spectrum, right? So we add. But if you can even write the equation other way around. So for example, if you have an unsigned number u, and this u is in this spectrum, that is u is less than this point, u is less than 2 raised power w minus 1 or equal to. This is the highest number on the signed encoding for w bit. If our number is less than that, that is this portion, the corresponding signed number is same. But if our number is greater, if it falls somewhere here, it's greater than this point, then you need to subtract 2 raised power w. I hope it's quite helpful now. Thank you very much.